So we've looked at ways of depicting compounds with our formulas. Now we're going to kind of dive into there and look at what's happening down on the molecular level as we look at elements and compounds. So we're going to be defining some terms that we use a lot, and students need to really practice this new language because I will use it assuming that you understand what I'm talking about. And I have seen in the past where we used one of these words on an exam and students missed the question, not because they couldn't do the problem, because they just didn't know the language that we are using when we talk about what these things, how these things exist. Okay, so let's start off by thinking about elements. When we talk about elements, we define them as having, all the components are made up of the same atom, and that makes an element. But those don't have to exist as individual atoms independent of each other. Sometimes these things occur as molecules. So when we see the word element, they sometimes exist as individual atoms. Now, all of your noble gases exist this way. Okay, when we look at the periodic table, the far right-hand side of the periodic table, you might want to stop and pull one out. But the far right-hand side of the periodic table with helium and neon and argon, those exist as individual atoms totally independent of each other. But that's not always the case. Sometimes an element can exist as a molecule. Now, students a lot of times want to use the word molecule only for compounds, but that's not the case. All it means when you have a molecule is you've got more than one atom that are joined together with the bonds. So if we see something like molecular chlorine, chlorine exists as a molecule made up of two atoms. When it's made up of two atoms, we use the word di for two, a diatomic molecule. So these are molecules that exist as two atoms. Those two atoms stay hooked together in the element chlorine. And whenever we're talking about elemental chlorine, we would always use that as the description of elemental chlorine. We would never use just Cl as a description of elemental chlorine because it always exists as diatomic molecules. Now, there's a lot of other elements out there that exist as diatomic molecules. There's some that exist as molecules with four atoms hooked together. So I guess we could use the word tetratomic, but we don't use that language. Okay, so that's elements. Now, your compounds. Compounds aren't always made up of molecules. And here's where, from last year, I can remember students not understanding some of the terms that we use if it's an ionic compound. Compounds are sometimes made up of molecules, and we call those molecular compounds. Sometimes compounds are ionic compounds. Okay, what's the difference? Well, molecular compounds, typically you have your nonmetals hooked up to more nonmetals. They are joined together and they actually exist as molecules, okay? And molecules are small, discrete little bundles of atoms hooked together. So when we see H2O, okay, hydrogen is a nonmetal, oxygen is a nonmetal. This would be in a molecular compound, and really what's happening here is an oxygen atom is joined together, and we'll put an O in the middle for that one, and we'll put some H's in the middle of this, and they're linked together like that, and they actually work and function as these three atoms together as individual molecules. Ionic compounds do not come in the form of molecular compounds. Ionics don't have discrete molecules, okay? Now, typically, we're going to have ionic compounds that are considered joining together of metals with nonmetals. You need to know that they are, and I'll write it really big here, they are not molecules. They are not molecules. So what are they? Well, we'll give it a name for them here in just a little bit. Okay. On the left, and I promise I will get a name for it here in just a little bit. On the left, we have our elements, okay? And we have on the right our compounds. Those are the two categories of pure substances. They can either be elements or they can be compounds. We learned about that in Chapter 1 when we were talking about how we categorize matter. Okay, so elements can be further categorized into being atomic, and those are our noble gases, typically as a good example, and we have neon as an example here. Or they could be elements that are molecules. Earlier I gave you an example of Cl2. Well, here's another example of a diatomic element, oxygen. It is O2. So that's what we have on the left. And over here on the right are our two categories of compounds. They could either be molecular, and notice here how we've got these little units, okay, and our chemical formula will describe that unit, how many of each atom are in there, and it's a nonmetal to nonmetal connection there, and we have got ourselves a molecular compound. Over here we have sodium and chlorine. Sodium is a metal, chlorine is a nonmetal, and they don't come together typically to form molecular compounds, but ionic compounds. Now, ionic compounds are large three-dimensional structures that go off in all directions in three-dimensional space. They're not small, discrete units. And when I write a formula like NaCl, this formula is an empirical formula. It is the lowest whole number ratio of those atoms, because if you ever looked at table salt, and that's what sodium chloride is, table salt, and you looked at it in your hand, you would see little bitty cubes. There are so many atoms next to each other, a sodium next to a chlorine next to a sodium, going off in all dimensions until it's big enough for you to actually see. It means there's a lot of atoms there. So we don't use a molecular formula, all the sodiums and all the chlorines. That'd be like Na 4,632,000,000, Cl 4,632,000,000. Who would want to write a formula like that? So when we see NaCl written, what we are writing is called not the molecule of sodium chloride, but a formula unit of sodium chloride. So anytime we're talking about ionic compounds, we could talk about its formula unit. NaCl, here's an ionic compound, FeS, or FeCl2. That's a metal, non-metal. They exist in this three-dimensional network that's big. And we would say this represents one formula unit, not one molecule of iron chloride. This would represent one formula unit of iron sulfide, not one molecule. So the word molecule is applied only when it's a molecular compound, not when it's an ionic compound. Now, there are certain elements that I expect you to know that are diatomic as an element, okay? And they're in yellow on this periodic table. There are 7 of them, okay? And so we have hydrogen as the first one, okay? And I'll give you a couple ways of remembering this. You got to get hydrogen in there, and there are 7 of them. So start with element number 7 and make a number 7. How about that? Okay. So if you're looking at a periodic table, you can quickly pick out which elements exist as diatomic. So if you're visually kind of gifted with visually seeing things, maybe that is one way to think about remembering which ones are diatomic. Another way to think about which ones are diatomic would be for those of you who are more auditory. There's a word that I'll say first, and then I'll try to spell it, okay? The word's Hofbrinkel. Now, some of you might have learned some other words along the way, because I've heard another one, I just can't think of what it is. But Hofbrinkel was the one that I had learned. Hofbrinkel, if you can spell it, tells you which elements exist as diatomic. All right, so HOFBRINCL, okay? So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Those are the elements that exist as diatomic. Now, what does that mean? That means if somebody says, I'm handing you a jar of oxygen, it's the element oxygen, and you would write O2. They said, okay, here contained within this container is some hydrogen gas. It would be H2. Now, does that mean that every time you run across an oxygen, it should have a 2 subscript? No, because oxygen could be in a compound. So here's an example of oxygen in a compound, right? Do we have a subscript of 2 with oxygen and water? No. If we had a compound, let's say, here's iron 2 oxide. I'll teach you how to name those later. Okay, it doesn't have a subscript of 2. So don't think every time you see oxygen it has to have a subscript of 2. If it's in a compound, it might be all sorts of subscripts, okay? There's a Fe2O3, a different iron oxide that exists out there. Doesn't have a subscript of 2. But anytime you're running across elemental oxygen, it is the element oxygen, and that's what you're reading, oxygen gas, it's going to be O2, all right? All right, so you've got to have those committed to memory, because as we write formulas and we start writing chemical equations which represent our reactions, we're going to make sure we write these correct formulas as we go through it. Okay, so I've mentioned some of this. I just want to pound it home. Ionic compounds are not made up of molecules. Don't use that word with ionic compounds, or if you use it, understand you are being a little bit loose with your language. Ionic compounds have this three-dimensional structure that we see here in our picture. The sodium, and the sodium is actually the purple one, and the chlorine ions, these are actually ions that we'll talk about more. These ions keep going off in three-dimensional structure, okay? So that is not a molecule of sodium chloride, and we use the term formula units when we're talking about that. Just keep that in mind. If we talk about something that is non-metal to non-metal, it's more likely if it's non-metal and non-metal, it's more likely to be a molecular compound and actually is made up of molecules. But if it's a non-metal and a metal, then it's more likely an ionic compound, and we would describe the smallest unit of that compound as a formula unit and not a molecule. All right, everybody dislikes this table, okay? Just accept this fact, because there is sometimes a lot of memorization we have to develop as we're building our foundation of the language. We're learning a language as well as learning chemistry, because that's just the way you study something, is to know the language. So this is a list of some common polyatomic ions. This is the list of the polyatomic ions that you have got to know. You have got to commit these to memory. So, what is a polyatomic ion? It is an ion, meaning it has a charge, okay? So these things have charges, and it consists of two or more atoms within the ion. So let's just examine one for just a moment. NH4. NH4 is a nitrogen with 4 hydrogens attached, okay? So I'm showing you the structural formula. Now, what about that positive charge? This whole thing, complete thing, contains a positive charge. So it's not like the plus charge is sitting on the hydrogen or on the nitrogen. We'd say that whole ion has a positive charge, and then it could be within an ionic compound attracted to something that had some negative charges associated with it. Now that's not a, that's got 5 atoms in it, polyatomic. Here is another example, Cn-. The C, now you don't need to know this yet, but it has a triple bond to the nitrogen, and this whole thing contains a minus charge. So that is 2 atoms. We could call it a diatomic ion, but we just use the word polyatomic for all of these. Okay, so that is what a polyatomic ion is. Now, what do I expect you to be able to memorize from this list? You've got to know everything you see on there. You need to know the formula name and the charge of each one of these formulas. So that if you're reading along and you see the word nitrate, okay, in something that you're reading, or you hear me use the word nitrate in our lecture, you need to know that it is NO3, and you need to know that it has a -1 charge. That's what you have to commit to memory. If you were looking at a formula and you saw something like Na3PO4, okay? If we look at that right there, we can see this thing in our table. That is the ion. So we should know 2 things about it. We should know its charge, because it's not written when you see a formula. Charges are not written for compounds. They exist, we just don't write them in when we're writing the full ionic compounds formula. Okay, so we need to know its charge is 3-. We also need to know, when we see that, its name is phosphate. That's an O. Okay? We need to know that about it. So there's really 3 pieces to know. There is the name, There is the formula and there is the charge. If you know the name, get the formula and charge. You see the formula, get the name and the charge. All three of those. If I could figure out a way to make a three-sided flashcard, that'd be great. But that's what you need to know from this list. All right, now this list is kind of put out, grouping things together with similarities. So if we look at, these guys, there's some similarities between them. So let's look at, it's not a great system, but there is a little bit of a system to these things. Let's see what that system is, all right? So here is just kind of breaking down some of the things that you'll see, because if you can memorize just a few things and then make these connections, you can make these connections in multiple places. Okay, so let's start by, when you're looking at the list, anything that has an ATE ending, I recommend that that's the one that you just flat out memorize. Okay, so you run across in the table and you see, I've got the word carbonate. I'm going to memorize carbonate is CO3 with a 2- charge. Now there is nothing about this ending, ATE ending, that tells you how many oxygens it has. Doesn't tell you that. And it doesn't tell you the charge. Okay, it just so happens on this one that the chlorate also has 3 oxygens, but that's not always the case. You memorize the one that has how many oxygens the one has, okay? And you can see right off the bat that the ATE ending doesn't say anything about the charge. You just flat out have to memorize the charge. If you look back at the full table, actually I'll go ahead and pull it up here. Here is phosphate. Phosphate, that's the ATE ending one, has 4 oxygens. I have to memorize that. Phosphate is PO4. I have to memorize it has a 3- charge. So memorize the ones that have the ATE ending. And then we can make connections to the other guys. So let's see what those connections are. We're going to learn them kind of bit by bit. Let's start with, if you memorize the ATE ending, and I'll put a red arrow next to it, okay? Then you memorize that it's CO3 with a - charge. If you put a prefix of per in front of it and it becomes perchlorate, what you do different with the formula is you add an oxygen, as we see written there in my red box. Between the 8 ending that you memorize and putting a per prefix before it, you end up having 1 more oxygen. Now, did it change its charge? No, it's still got that -1 charge, so once you have that chlorate is ClO3-, perchlorate is going to be ClO4 and still minus. Okay, let's go and do less oxygens. If we take, got to go this way. If we take 1 oxygen away, minus an oxygen between chlorate that you've memorized, when you change the ending to ITE instead of ATE, ITE has 1 less oxygen, so it's ClO2-. And then if we want to go even more, 1 more less than that, it would have a hypo prefix. So it still has the ITE ending, but it's got the hypo prefix, so hypochlorite. Now the example with the chlorines, the 4 that we see right here, we won't see that for everything. Not all polyatomic ions have all of those choices. But let's go back to our table and let's see the choices kind of play out where we see it. So I'm just backing off a little bit. Okay, let's compare these two here, nitrite and nitrate. If you have memorized that nitrate is NO3-, flat out memorize that, then it's easy to understand, if you understand the rules, that the one with the ITE ending will be 1 less oxygen. So nitrite is NO2-, but contains the same charge. Okay? We see that with the sulfate and the sulfite. All right, so now there's another connection that we're going to see here. Let me flip through until we get to it. All right. With this, once you've memorized the ATE ending, sometimes all we do is we add hydrogen to it, okay? So from what we see here and what we see here, we've added an H. Now what we need to realize is what we really added is an H+, an H that has a positive charge to something. So if it had a positive charge and we added it to it, that's going to take a 2- down to a 1, because 2- plus 1 gives me a -1. And the way we name that is we either put the hydrogen in front of it, so this thing could be called hydrogen carbonate, that is an absolutely fine name for it, or we put a bi in front of it, bicarbonate. So that is also an acceptable name So I don't know why, but this guy gets two acceptable names for it, hydrogen carbonate or bicarbonate. So you have got to commit them to memory. This is just some little connections to help you so it's not all pure memorization, but it is a lot of memorization that you've got to go through in order to get those in your mind. And you will have to know them and use them throughout your general chemistry experience, okay? So don't just kind of put them in there and throw them away. Put them in there and review them commonly so that you get it into your long-term memory instead of your short-term. I said commonly, I don't know what that means. Review them often so that you get them into your long-term memory and not just your short-term memory. And it's not something that you memorize for this test and then you forget forever, ever. You need to know that language. Now, let's practice it. I've given you some connections here. I've made up some ions, okay? So, let's say that there's this imaginary element, okay, which is the abbreviation AB. And the one with the ATE ending is abdicate, okay? So abdicate has a 2- charge and it has 2 oxygens. So which one of, what would be the name of this guy? Stop, review those connections I gave you, and see if you can come up with a good name for this one. Well, if all you change was the suffix to ite instead of ate, you'd be correct because it's 1 less oxygen. So there would be abdicite. Okay, I made that up, so there you go. Actually, it's supposed to be abdicite if you're going to follow our English rules. But there you go. We have the connections for 1 less oxygen, change the ending to ite. Okay, how about if this guy is abdicate, which we said there be, could there exist an oxyanion? Now, what do I mean by oxyanion? An oxyanion is an anion, so it has a negative charge, okay, that has oxygen in it. So all of these things and their connections, these are oxyanions that we've been talking about. So if there was something called abdicate, and it was AbO2 with a 2- charge, could there be one called hypoabdicite? See that C-I-T-E, I-T-E ending there? Think about it. Come up with an answer. And let's see what you got. Number 3, what a stupid question. Well, yeah, there are a lot of people out there who think hypothetical worlds are stupid worlds and nobody should talk about them, but we're having fun with this, so I don't buy into that. I like to talk about hypothetical things here. So we're going to get rid of that one. Yes, of course, and no way. Well, I would say the answer is, well, let's see what the answer is, all right? What did we say abdicate would be? It would be AbO2 with a 2- charge. Abdicite would be AbO with a 2- charge. And hypo means you take 1 more oxygen away. So we have AB. Well, is that an oxyanion? No. And so he would not follow our rules. He would be called hypoabdicite because it's not an oxyacid or oxyanion. We only use these connections if there are oxygens there. So there couldn't exist this guy. Could there be, just another question here, could we, if this was abdicate, could there be something called per-abdicate? And that really, there shouldn't be a space there. Per-abdicate. Could this exist? And if so, what would its formula be? Well, once you've memorized abdicate, dang it, I forget. Let's see. Which way is this going to go? There we go, there we go, there we go. I'm going the wrong way. Okay, sorry. Per-abdicate would be 1 more oxygen, so it would be AbO3, and it would contain the same charge, so 1 more oxygen than the one with an ATE ending. So yeah, it could conceivably exist in this hypothetical world, and that would be its formula. Okay, so we know the difference between molecular compounds and ionic compounds. We understand that elements can be either atomic elements or molecular elements. existing as molecules. We've got a list of polyatomic ions that we're just going to have to sit down and commit to memory, and we've seen some connections between those ions here to try to help in that memorization. Start now memorizing those, and we'll see how you do with it as we progress through this class.